Hello, good morning. Welcome to the class ECE451, the control engineering. Today we will discuss a special kind of control system. The controller we call is a PID controller. PID controller. This kind of controller is applied in a lot of industry field. Yeah, so very useful one. Very useful one. Right. ECE451. Oh, reverse. It turned around. Okay. It's a fourth week. It's a Wednesday class. Okay. We consider the PID controller. PID controller. PID controller. PID controller looks like this. D of S are equal to three part. First part I call it Kp, a constant, and then Ki times 1 over S and Kd times S. So here this Kp, this is a constant, so this is kind of proportion, and this one 1 over S is integral, right? Integral. So this is a Pi, and the D is a derivative. Derivative. So the controller has these three part, and then the whole system will look like this. We have a D of S as a controller, and the plant G of S, and the feedback. Yeah, here we can just consider the most basic style. It's a unit feedback. Okay, it's plus minus. The input is R of T, and output is Y of T. Yeah, things like this. And if you want more details, here you can have a noise. Yeah. So this is a PID controller. PID controller. For PID controller, we have 3 parameters we can choose. So this one is better than you just use just a constant. Yeah, actually we have 3 kind of them. The first one is only with the proportion. So it's a proportional control. So that means this Ki and the Kd, they are zeros, right? The same ds, but these 2 parameters are zeros. We only have Kp. And the second style is P and I. So it's a proportional plus integral control. So it's a PI control. This is the case. We have P and I, we can choose different value, and no KD. And the third one, of course, is overall. We use, or that's three part, Kp, Ki, and Kd. Right? We use all 3 of them. Actually, this one during the industry, during the practice, during the real application, people found it can be applied almost everywhere, all the industry field. So because you have three parameters you can choose, then most feature of the system, you can reach your requirement, right? Reach your requirement. So there's a use a lot. Of course, choose 3 parameters is not so easy. Basically, we only have the method is try a set of parameters and see how it works. If it is good, okay, you're fine. If it is not good, try another one. If you are lucky enough, you can find the right parameter in like maybe a few hours. If it is you are not so lucky, maybe you need to spend maybe like several weeks or even several months to find the right parameter. Oh, that would be terrible. Huh? So then people, after so many works, people also find a way to find a way to start work. Yeah, you can start from that kind of parameter, and which will be maybe it is not very good, but at least in most cases that method will give you parameters at a set of parameters. It is close to the good one. All right, so that is a method how to find parameters, find K, P, K, I, and K, D. Now we call this is a Ziegler, Nicholas, 2 people. They gave this method. Of course, a turning. Yeah, like a turning. You have a instrument. The music is instrument. You're turning to find to make the voice good, right? Make the sounds good. Yeah. There's 2 cases. The first case, by the based on the step response of the plant. So you check this G of S. Suppose we have these things look like this. This is a G of S, the step response. Step response of G of S. Suppose it looks like this. Then we can have several values. One in the steady state, we use a notation A to denote it. And then we have like here you think it's a setting time, right? You have setting time, and here you have in the beginning it's small. Then when it starts to grow up, you have another time. Okay, so we call this time as L, this time as tau, and here I use different color. We combine these. I have a straight line, Okay, then this straight line, it has the slope. It is R equal to A over tau. Right. So this line has, here's a tau, right? Here's A. So this one has a slope. So when you have a step response of the plant, you can have these 3 values. Of course, it is not so exactly, because where you choose these 2 points is somehow different people can maybe have different value, and even same people, the same guy, if he do this different times, then maybe every time the value might be a little bit different. But doesn't matter. This is a kind of estimation. Then after you get these 3 values, then we can have a formula to find the parameters. They are in the textbook. Let me show you. I opened it here. Yeah, this is the graph. You see, this is the graph. It's a step response, and you have these several values: the slope, the steady state, the setting, and kind of a rise time, right? Something like that. And then after we have these values, the formula is here. So we can determine those coefficients. We have three cases. This is table. Let me copy it. Table 4.2. This is 4.2. Table 4.2. Huh? Yeah, table 4.2. Make it smaller. Okay. Yeah. Then let me copy here. So we have two columns. One is a type of controller. One side is the parameters. This is gain, optimal gain. If the controller is a P controller, the proportion controller, so just contain K. If we just contain K, then I use that K. The Kp is 1 over RL, right? R is here, the slope. L is the time, right? The time when the step response start coming up, right? Is L. And this is one case. If it is the controller is a PI controller, so we need two parameters. So one is a Kp, which is 1.2 over RL, and then we have 0.9 over RL, and then we have a Ti equal to L over 0.3, and here Ti is a parameter. It's here. You see, where d of s written as parameter k, that is Kp actually, okay, times 1 plus 1 over Ti times s plus Td times s. Oh no, the s is denominator. 1 over Ti times s and the Td times s. Look at this. Alright, so here Ti is this number. If you use the notation here, this one is this Kp over Ti. Right? This one is Kp over Ti. Yeah. Okay. Yeah, I have in the beginning I write in this way, right? The controller. So this one is Kp over Ti. Kp over Ti. Kp over Ti. This is second controller. And then the PID controller, then we need three parameters. The Kp is 1.2 over RL, and the Ti is 2L, and we have a Td, which is half of L. So this is the called like optimal gain. So in most cases, this set kind of parameters, it works fine. Maybe they are not the best one, but it really work. And in a lot of cases, they are almost close to the best one. Yeah. Okay. So this is one way. So based on the step response. But this one you need a requirement. This is step response. You have a steady state A. So that means the system should be a stable one. The plant should be a stable one. Right? Stable one. You have a step response. If the plant is not stable, then the step response maybe go to infinite. Then you cannot have A. So here we suppose G is stable. Then you can have A. A is smaller than infinite. Right? Maybe negative value, things like that. So we need this as a requirement. Right? Okay. Then the second way, we use based on the impulse response. Impulse response of this one, I say this is a T1 of S, which is kg of S over 1 plus kg of S. So this is the impulse response of the, you only use a proportion control, right? Proportion control. You have a K, then you have a G with a feedback, right? This way. Then this, I call this T1, right? This is T1. This is T1. The T1 in this, right? T1 in this. Sorry. Yeah, based on the impulse response of T1. Yeah. And by this one, for different K, the graph, the impulse response might be different. So we need this method. We need two steps. Step 1: find a value K equal to some Ku, so that T1 of S is marginal stable. That means the impulse response of T1 will look like this. It will not go to infinite, but it also will not go to 0, because this is the impulse response like this way. This is marginal case. If you use a larger K, usually this will tend to be 0. If you use small K, this might be go to infinite. Okay. So you can choose that K. You find that Ku, and then at here you can check one period. This is one period. You have a period, right? You have a period, and you have this value. You have this one is a Pu. It's one period. One period. One period. Okay. We have these two numbers. We have these two numbers. Then we choose the PID based on these two numbers. They're also in the table. This going down. This is here. Yeah, this table. This table. Then by table, this is table. For the 3, we still use this one, the D of S, which is Kp times 1 plus 1 over TIS plus TD times S. We still use this notation. And then enough space. Okay. Then for the type, I write this one. PID control, just Kp, right? This is a half of Ku, the PID control. And PI control, then I need a Kp, which is half, not half, it's 0.49 Ku. And Ti equal to Pu over 1.2. And then PID control. Yeah, I'm copying just that table. It's a just this table. It's a Kp equal to 1.6 Ku, and Ti equal to 0.5 Pu, and Td is 0.125 Pu. Alright, so we can choose these parameters by this way. Usually you use these parameters, then the whole control system will have kind of a nice behavior. It is stable. It is like the regulation type and the tracking type. They also higher than others. Okay. Yeah. And if you check the step response, then the overshoot will be a value not so large, and the setting time is not so long. Yeah, something like that. Okay. We can try the second part. Yeah, this part we can have a try. Use MATLAB. Let's go to the MATLAB. Okay, let's s equal to transfer function with just s. Just s. I give a s. Then I define g, which is I think I have this one, right? Okay, I use this as g. G is the plan. This is the plan. This plan, we can see the step. Yeah, PG map of this G is unstable one. Okay, see the cross here? Make it right. Yeah, here's a cross here. So this is a 1 plus 3i. According to this pole, the system is unstable, right? And another one is here. So two poles, they have positive real part in the right half plane, right? So it's unstable. And I have 0 here, -3. So this is unstable system. You can also try, if you want, you can see the step response of this G. Yeah, I did this one. So you see the value of this step response will tend to be larger and larger. It's kind of a sine wave, but the amplitude is increasing. So this one you cannot use the first method, right? We have two methods. Here we have two methods. First method, you need a step response. But now the step response turn to be like never stop to a steady state. So we cannot use the first method. So we can try the second method. Second method, I use a k equal to, firstly I just put any value. I just put k equal to 1. Alright, k to 1. Then I consider a unit feedback system. The unit feedback system with control just that k. So I say this is T1. I have k times g, as is the numerator, and the denominator is 1 plus k times g. Right. So this is a feedback system. And we can look at the impulse response of this T1. What it is. Okay, for K1 it is still unstable, right? Start from 1, then go to negative side and positive side, but the amplitude, obviously, the amplitude tend to be larger and larger. So we want increase K, like I use 10, but it works. Step response. Okay, now the step response tend to be 0. So this is the stable case, right? This is stable. It is stable. And we want to find the boundary. We want to make it the marginal case, right? So marginal, so that will be a value between 1 and 10. So k equal to, now I use k equal to between 1 and 10. I choose 5. Yeah, we can try one by one. Okay, this is still stable, so I need a value smaller than this k. This I choose the middle, 3, just 3. Okay, 1 and 5. 1, 5, 6. 1 plus 5, 6. The average is 3. Right? Use 3. Okay, yeah, this is close to the marginal case, right? The amplitude decreasing, but not so fast. Okay, it's almost close. I think 2 might be work. I choose 2. K is 2. Now the feedback gain is 2. Yeah, I get it. You see? So this one is a marginal case. That means when k is 2, the system is in the marginal stable case. And then we can find the period from this one. Can we find the value here? Okay, this time is a second 0.556, and here this point is 2.12. Then the distance between these two values, we have that we call the PU, right? The PU. This is PU, right? This is PU. So now, yeah, right. Example. I have g of s, which is s squared minus 2s plus 10. And what's the numerator? I forget. I have a pole at 3. Yeah, negative 3. So it's s plus 3. And use k equal to ku, which is 2. Then this one, the feedback, unit feedback system, Ry. This one is marginal stable. And the impulse response, of, let's say this is T1. Of T1, it looks like this one, right? This one. And we have time. This point is t equal to 0.556, and this one t equal to 2.12. So we have PU is 2.12 minus 0.556. What is the value? I need. Okay, I just write. Yeah, 2.12 minus 0.556 is 1.5640. Okay. So we have PU. And KU is 2. So we can choose different parameters for those three controllers. For example, if we consider PID controller, I use KP. KP will be this one. KP will be 1.6 times KU. KU is 2, so this 3.2. And TI will be half of PU, is half of these. There will be 0.7820. And TD is 0.125 times PU. PU this one, 5640. It will be, I need to calculate. So this is the answer, right? And just divided this one times this one times 0.125. This is 0.1955. Alright, I can use these three numbers to give these three numbers give a PID controller. Right, we have these three numbers. So I can use a DS like a D equal to KP. KP is 3.2 and times the 1. Oh, not 8. It's times 1 plus 1 over. The inside will be TI. It's 0.782 times S, right? And then plus 0.1955 times S. 1, 2, 3, 4. Okay. Are we good? Oh, too much? Okay. So this is the PID controller. I have D is that PID controller, and I can use that like T equal to. I use this as feedback as a controller, right? It's a feedback, so it will be D times G over 1 plus D times G. So we can have this one. Okay? Oh, is it okay? I use lowercase for G. It's a very large one. Okay. So the whole transfer function T, this one, we can see what is the step response of this T. Looks like this. It is still not so good. Let me see. It is D times G over 1 plus D times G. Yeah. So we have a controller looks like this. But at least this is a stable one, right? The original system is not stable. Now it is stable one. I have a stable one, and then you can, based on this, you make some changes. Actually, PID controller, it is studied. It is related not just for the stability or the maximum overshoot or like a steady state error. They also related with the tracking and the regulation problems. Remember, last time we have discussed that. Yeah. Now we can have a look about that. Okay, I think I don't need it. Do I need it? Anyway, I leave it here. Okay, now let's consider what happened when we use a PID controller in the problem of tracking and regulation. Right? I use consider example. I will compare PID control, proportion control, and the PID control. I compare these two, and the plant, I choose a plant G of S equal to like S squared plus 2S. Here's a 1. Yeah, I use this as G. This as G. This one has a pole. One is 0, one is -2. So this one is a marginal stable, right? G itself is a marginal stable. Marginal stable. Here the pole along the imaginary axis is this one, just 0. So if input is a unit step, That 1 over s is a unit step, right? If input is a unit step, the output will go to infinity. You have square of it, right? If your input is 1 over s, then the output will contain 1 over s square term. This is a 1 over s times s plus 2. So if input has 1 over s as input, then the output will have 1 over s square. That give us t. Give us t. You can see step response of 1 over s plus 2. We can look at this. Yeah, this is step response, right? You go to infinite. So this is an unstable one. We call it marginal stable. Right? Sometimes you can also call it marginal unstable. Basically, it is unstable, but we use the name marginal stable. Marginal stable. Now, if we use T1 is you just use a feedback, use a K, the proportion controller. And the T2 is let's say is a D. Right. This is a T2. We want to compare these two. For T1 of S will be Kg over 1 plus Kg. So it's a K over S squared plus 2S. This is the numerator. Here's a 1 plus K over S squared plus 2S equal to is K over S squared plus 2S plus K. Okay, so for this one, for the stability, you need to check the location of the poles, right? The PZ map. No zero, two poles. The poles, the real part, the poles will be s squared plus 2s plus 1 plus k minus 1 equal to 0, right? So this is s plus 1 squared equal to 1 minus k. So s equal to s plus 1 equal to plus or minus square root of these. So s equal to here's a plus, that side is negative 1 plus or minus square root of 1 minus k. This one, if k is a value less than 1, k is less than 1, this side is positive, then you square root of it, so you have two poles on the real axis. And if k is larger than 1, then you have imaginary. This is the imaginary part. The real part is always negative 1. So the location of the poles were on the real axis, and here's a negative 1. So along this line, and this cross, kind of cross, along these red lines, the pole will be somewhere here, or somewhere here, or somewhere here, or somewhere here. So when you choose different k, the poles will move along these two lines. So this is your choice. For this system, you choose different k. You can put location, put the location of poles at different place, but just on these two straight lines. You cannot put here or put there, right? Yeah, it's kind of a one-dimensional choice, right? All the choice of the poles are along a line, straight line. Okay, this is stability. And then for the tracking, I need to write more. For tracking, then the input is I use t to the n, t to the k, and in S domain, okay, I suppose here is S to the k plus 1, and here I need a parameter k factorial, I believe, or over k factorial, things like that. Yeah, you check table to make sure what it is. Alright, some constant here. You put some constant here, then make RS is 1 over S plus 1. RS is this one. Then for checking, we want E of t, which is R of t minus Y of t, and ESS will be the limit t go to infinite of E of t. Then we use the status error, right? We use the calculation in the S domain. It will be S tend to be 0. This S times capital E of S. The capital E, this one is capital R minus capital Y. The capital Y is T1 of S times R, right? The system is here, T1, right? T1. So this is a limit S tend to be 0, S times R of S. Here is 1 minus TS. This is TS, 1 minus TS. So 1 minus TS, 1 minus T1. And the T1 is here, T1 is here. S squared plus 2S plus K, here's K. And this one is 1 over S to the K plus 1. So it is, I cancel 1 of S. So it's a limit S tend to be 0, 1 over S to the K's. And this part is, denominator is S squared plus 2S plus K. And numerator is S squared plus 2S plus K minus K, right? Plus K minus K. So they cancel. Okay. Then this one, this part I can write as S plus 2 times S. And when it go to 0, S tend to be 0. This will be S over SK, right? This S and this SK, I put it here. Then S plus 2, S go to 0, that is 2. And denominator S tend to be 0, this will be K, right? So you can write this way. And this part determine whether the value is infinite or constant or 0. So we have 3 cases. If K is larger than 1, you see, if K is larger than 1, then S tend to 0 give us infinite. If K is 1, then they cancel. So I have 2 over capital K. Oh, I have 2 K's. This K, the capital K is the feedback, and the lowercase k the power in the T. Alright. Yeah. Okay. And when K smaller than 1, K smaller than 1, K smaller than 1, then it will be 0. Right? It is 0. So the type, the tracking type of T1 is what? Is 1. Right? Is 1. Is 1. No matter what is the K. Of course, K cannot be 0. K cannot be 0. K cannot be 0. Make sense? Yeah, if you put K0 here, then it's nothing, you know. The input go to here, then vanish it, K0. So no input totally. Yeah, so K must be a number do not equal to 0. Yeah. Okay, so this is for tracking. And we can also check the regulation. Regulation type. Now is the input like this. We consider the noise as input, kind of. Noise here is W of T. Right, like this one. Here's R, here's Y. For regulation, you can just think the input R is 0. You only have noise as input, and you want the output will tend to be 0. So that means no, the noise will cause no mistake in the output. Of course, that means for long term, the steady state of the output tend to be 0. So now you consider the input is W and output is Y. You consider the transfer function. This transfer function, how to get it? Now we have a loop here, right? And the forward path from W to Y is this one. So by the gain formula, forward path it is just G, and the loop is 1 minus the loop gain is negative K times G. It is this one. Remember, for regulation we have another style. We use a reference, R as reference. We use minus positive. We use E. I want this E tend to be 0, or Y tend to be 0. Here if R is 0, and this one doesn't matter what is R. Same thing. If you use this one, then here will be E over W, E over W, E over W, E over W, and E over W. Then the forward path is still this one, but you have negative here, so the numerator will be negative G. Yeah, and then the loop is same loop. We only have this loop, right? Yeah, it will be same thing. And this path, if you consider W as input, this path is nothing. The input side, input W just go along this way, then to the output. Never go to here, right? Never go to here. You go to this way to E. If you go to here, they will tend to the loop, and okay, go back to E. Never go to this path. So never go to the lower path, right? Yeah. Then the transfer function will be negative. Now I use this. I use G here. Okay, I have Y is this, Y over W is this, so Y will be G over 1 plus Kg times W, where W is W of S is 1 over S K plus 1. I suppose this one. Then we have we want a limit. I say ESS. I still use this notation. E is arrow, right? Arrow SS. T to infinite. This is Y of T. Then this will equal to limit S tend to be 0, S times Y of S. And okay, plug in S times Y. Y is this one. Y is this one. It is a G over 1 plus Kg times W. And W is this, so it is 1 over S to the K plus 1. And okay, this is the limit S tend to be 0, and I put these two together, that is 1 over S to the K. The plus 1 cancel, right? Plus 1 cancel. And the G is 1 over S squared plus 2S and 1 plus K times K times G, 1 over S squared plus 2S. So this is a limit S tend to be 0, 1 over S to the K, and this part it is 1 over S squared plus 2S plus K. Yeah, S tend to be 0, and this part will be 1 over K, right? So it's 1 over K, and the limit S tend to be 0, 1 over SK. So this value, it will be 1 over K if lowercase k is 1, is 0, right? If this is 0, the 1 over 1. Then it's infinite if k is larger than 0, or larger than and equal to 1, right? So that means, when k larger than 0, it's infinite. When k less than 0, yeah, you can try less than 0, there'll be 0, right? So anyway, the type is the regulation type is 0. Is 0. All right. So now we are clear what happens if we use proportional control. Proportional control, for stability, how to choose the poles depending on K, right? Depending on K. You try to find the K located in the left side, then you can make it stable. And for the tracking and the regulation, the tracking type is 1. Tracking type is 1. And regulation type is 0. Okay, so this is for the system with the controller K. Now we consider T2, right? I said T1 and T2. T2 will be T2 of S will be dg over 1 plus dg, and d is k p plus ki over s plus kd times s. So this one equal to, let's say it's kp plus ki over s plus kd times s times g. G is 1 over s squared plus 2s. Right? What is my g? G is here. Yeah. G is here. Right? I use this g. And then 1 plus d. This is d. I just copy over s plus kds. And g is 1 over s squared plus 2s. Then this one I times s and s squared plus 2s in both numerator and denominator, right? I have this s, I have this one s squared plus 2s, so I times these on both numerator and denominator. Then numerator become, this one cancel, right? And this s also cancel, but here I have s, and here I have one more s. I put the s squared in the front. So this is kd s squared plus kp s plus ki. Okay, this is numerator. And the denominator, 1 times that is s cubed plus 2s squared. Right, 1 times this. And this part time it, s squared term cancel. And this one will be same with numerator, right? So same. So it is a kd s squared plus kp s plus ki. Let me write again. It's kd s squared plus kp s plus ki. And s cubed plus, now I have 2 terms with s squared. I put them together. That will be 2 plus kd times s squared. And then the linear term kd times kp times s and ki. Okay, the transfer function, the overall transfer function with the PID control, with the PID controller looks like this. Now you see 3 parameters are located in these 3 coefficients before s squared, s, and 1. So what that means? That means we can choose kd, kp, ki so that the poles of T2 locate anywhere. Locate at anywhere. Anywhere. Yeah, locate at anywhere. Right? Yeah, so that the poles of T2 they locate at anywhere, because these three numbers you can choose. You can put them to be any number. So you see, this time we have more choice for the poles, location of the poles, right? This is one thing. Secondly, for the tracking, similar thing. We want this one. We have R as input, D, then G, go out, say this is the feedback, plus and minus, this is y. We want to check ET equal to R minus y, and the ESS will be limit t go to infinite, this E of t, where R will be something times, I think it's k factorial times t to the k's, and then we have R of s is 1 over s to the k plus 1. If this is the input, then what is this one? What is this one? Okay, this is a limit s tend to be 0. I go to the s domain to the calculation. So here will be s times capital E of s, and so this will be so ESS will equal to limit s tend to be 0, s is still s. E is R minus y. So S domain is Rs minus y. And y will be input times the transfer function, that is T2, right? T2S. Okay. S tend to be 0. S times both term we have R of S, so I can move it in the front. This is R of S. And then it's 1 minus TS, T2S, 1 minus T2S. And the T2S is here. This is T2S. T2S is this one. T2S. T2S is this one. So it is 1 minus this one. It is S cubed plus 2 plus KD S squared plus KP S plus KI. This is denominator, and numerator is KD S squared plus KP S plus KI. So do a simplify. S cancel 1 is 1 over S to the K's, and 1 minus it, so the fraction, the denominator will be the same thing. Okay, I just copy it. And the numerator will be denominator minus this, right? Denominator minus this. So S cubed and 2S squared, right? Then KD term cancel, KP term cancel, KI cancel. Okay, so just like this. Alright, you see, I have S squared. So this is S squared times S plus 2. And S squared can cancel with cancel something with K here. So this is the limit S tend to be 0. I say is okay, I just put like this. S squared over SK. If K is larger than 2, you can cancel something. And this side is S plus 2 over S cubed plus 2 plus KD times S squared plus KP S plus KI. Now S tend to 0. S squared over SK, I keep it. And this part, S tend to be 0. This is just 2 over KI. Right? 2 over KI. Alright, we have 3 cases. K larger than 2. K larger than 2. Now after you cancel 2, you still have some S in the denominator. And denominator tend to 0. So this is infinite. And the K, lowercase k, K equal to 2, they just cancel. So this is 1. There will be 2 over Ki. And when K is smaller than 2, the denominator will be cancelled. You still have some S in the numerator. Then S go to 0, so it is 0. Okay, now we know the tracking type is 2. Okay. T1. This is for T2. For T2S. or T2S. Alright, this is a tracking, and then we also check the regulation. Now the graph of the system looks like this. D is the PID controller, and here we have some noise here, some disturb here. Go to the plant, and we have output. Input is R of T, and we have feedback. Here's a plus, here's a minus. This is a unit feedback. Then we need to consider Y over W. We need this one. This one will equal to forward pass is just G, and one loop is 1 minus that loop. That loop is negative G and D and G. And it's like this. And W, we suppose that W is also some polynomial, is a T to the K over K factorial. That means W of S is 1 over S to the K plus 1. Alright, so we have these, and we want to check the limit when T go to infinite. What is YT? We want to check whether this is 0 or not, right? 0 or not, or even infinite. Alright, this is a limit. Now S tend to be 0, S times Y of S. And what is capital Y of S? S is, I copy it. Capital Y of S, it is G over 1 plus DG times W, right? And W is 1 over SK plus 1, right? So this is W. This is a TS, T2S, right? Not T2, this is just this one, transfer function. Yeah, this one, right? This one, okay. Alright, let's plug in, do some simplify. S tend to be 0, and these two I can cancel 1 of S. I have S to the K's, and G is 1 over S squared plus 2, and the denominator is 1 plus D. D will be KP plus KI times 1 over S plus KD times S. This is a D, right? And the G is 1 over S squared plus 2. And times S squared plus 2 times S in both numerator denominator. This gives us, okay, limit I copy it. 1 over S to the K I copy it. And this part, numerator is S, right? This one times it, I get S. And denominator, I have S cubed plus 2S, right? S cubed plus 2S is here. I guess something wrong. Oh, I lost the S here. I lost, sorry, it's S. Here's S. Then here will be 2S squared. Yeah, 2S squared. Let me see. G of S. Yes, S squared plus 2S. 2S. I lost the S. Okay, so denominator will be 1 times this plus this part times S, right? So this is a KD S squared, this one, and then plus KP times S and KI. Alright, I have these. And okay, so now we have 3 cases. If K is larger than S, larger than 1, K larger than 1, then you cancel this S, but you have some S here, right? S go to 0, you use something divide by 0, so you get infinite. k is 1, then these two just cancel. This one and this one cancel. K is 1, they cancel. So we only have denominator. Denominator, let s go to 0. So we only have ki. So 1 over ki. And when k is smaller than 1, k is smaller than 1, k is smaller than 1, that will be 0 actually. Whatever. If you do you combine these two, you will have some s power in the numerator. So this gives us 0. Right? 0. Because this denominator, when s go to 0, it is always ki. Always ki. Right? Okay. So we have this one, and we say the regulation type is 1. Alright, regulation type is 1. Okay, now we can compare these two systems. Let me list the result here. T1 and the T2. Poles must be on that straight line, 2 straight lines. Straight lines, remember? This one and this one. This one and this one. Here's a -1, right? And this one, poles can be everywhere. Can be anywhere. You choose different parameter, you can put a pole at anywhere. Because we have 3 parameters for that 3 coefficients, right? You can always do that. And then for the tracking type. Okay. T2 has tracking type 2. This is tracking type 2. Okay, let me write this. T2 is tracking type 2, and this is also T2 regulation type is 1. And this is the location of the poles, right? T1. Okay, here. T1, the tracking type of T1 is 1. Is 1. And the regulation is 0, I think. Yeah, regulation type is 0. When you just have a K in the controller, right? The proportion controller. So this is the regulation. Zero. Alright, we have a result. You can see, obviously T2 is better. T2 is better. You can put poles to anywhere, what do you like. And the tracking type is 2. Tracking type is 2. That means if the input signal, the reference signal is the power is lower than 2, that means the power of 1 or 0. So it's a ramp input or a constant input, then the system can track it. And for T1, the type is 1. So only when the input is a constant, is a unit step, the output can reach the input. If input is a ramp, the output will also be a ramp, but always keep a distance. This is 1, type 1. That means when input is a polynomial with order 1, it's a ramp, right? Order just t. If t is the input, then output will be a value close to t, but will never reach cannot lost but cannot reach it. Yeah, I think I have calculated that P1. Yes, here, right? I have a 2 over K. 2 over K. This is a steady state arrow. So when the input is T to the K, T is a ramp input. With the ramp input, the output is also a ramp, but with the distance with the input. The distance, the arrow, the distance is 2 over K. So the output never really reach that, to touch that input. And there also always some arrow here, cannot reach it. Yeah. Okay. So for tracking, you can think this is a ability, a capacity of the tracking. T2 is better. T2 is better. And similar for regulation, when you have noise, when you have disturbed noise, for T2, if the noise is a constant, then by this one, the constant, that means the T to the 0 is smaller than this one. Then that means T2 can cancel that noise. The constant noise can be cancelled in the T2. This is very good, right? Very good. You have an input, you have a noise here. You have noise here, right? Noise here. If the noise is a constant, then after a while, in the beginning maybe the noise can make some change on Y, but when time is longer, in the Y side you cannot see what is the noise. No noise go to here. Noise will tend to be 0. Noise will be cancelled. Yeah. Now of course the order is just regulation order is type 1. So if the noise is a ramp input, that means the noise is increasing, right? This is T, increasing according to time T. Then the system cannot totally cancel the noise. However, the noise also will not cause the system give infinite output. Yeah, so this is nice. It's still nice. But for T1, it is not good. For T1, the regulation type is 0. That means if input side has some noise, even the noise is a constant noise, the output side you still have some noise here. Let me see. Regulation 0 for T1. And regulation type is here. Yeah. So if input K is T equal to 0, that means input is a constant, right? T to 0. Input is a constant. Then you count unit step. If the noise is like a unit step, then the output will contain the part 1 over K related with the noise. So the noise will cause a value in the output, that is 1 over K. And if the noise is like K larger than 1, the noise is like a ramp noise or even a parabolic noise, then in the output side will go to infinite. The noise will go to infinite. That will be terrible, right? So obviously, the behavior of T2 is better than behavior of T1. All right. So this is PID control. PID control. Okay. That's all for today, and then see you next time. See you next week. Right? This is Wednesday. The next class will be another Monday. All right. Okay. See you next time.